Okay, so I think we can start now. So welcome to the week 8 live session. So we will solve the week 7 quiz today. So the first question that is being asked is determine the principal component of the 2D data. So you have been given a pool of 2D data, and from there you have to find the principal component. So it should be actually the strength of the principal component, rather principal component, as because they are referring to the eigenvalue. Principal component is the vector that you basically generate from the eigenvalue. So it should be the strength of the principal component that they have asked over here. So nevertheless, we have been given the data. So let me just write the data over here. So we have been given the data in the form of x comma y, and the pool of data is -3 comma 3 -3. Then you have -1 comma -1, 1 comma 1, and 3 comma 3. So we know that to find principal component or to get the PCA analysis, we have to calculate the covariance matrix. So we have to calculate covariance of x comma y. So therefore, to calculate covariance matrix, so over there the formula to generate the covariance matrix is covariance is equals to x minus mu transpose. And as because we have been given a pool of data, so therefore we have to take summation of all these cases. So let us now find the mu, that is the mean of the data points. So mu would be, for both x and y direction, we have to calculate mu. So -3 -1 +1 +3 divided by 4. And then again -3 -1 +1 +3 divided by 4. So for both x direction and y direction, I'm calculating the mean. So mean is 0. It's a 0 mean data. Now we have to calculate the covariance matrix. So to calculate the covariance matrix, we have to follow this particular rule. So as because we have 4 different data points, so we have to carry out this particular multiplication of this x minus mu and x minus mu transpose 4 times. To do that, I can write it as, so in the first case, you can see the data. Now you can consider x, this x is 2 cross 1. and mu is also 2 cross 1. As you can see, x is in the form of 3, -3, -1, -1, 1, 1, 3, 3. And your mu is 0, 0. So there you can see all these x's are 2 cross 1, 2 cross 1, 2 cross 1, 2 cross 1. So as mu. Mu is also 2 cross 1. So what we will be doing is we'll be calculating x minus mu and multiply it with x minus mu transpose. So let us now calculate x minus mu for this first case. So 3 minus 0 over there it would be 3 and -3, 0, -3 minus 0. So it would be -3. Now we have to calculate the transpose. So the transpose will be 3. Sorry, this is -3. So it would be the transpose would be -3, -3. Fine. Then we have to calculate for this particular data. So for this particular data, it would be -1, -1, -1, -1. For the third case, it would be 1, 1, 1, 1. In the last one, it would be 3, 3, and it would be 3, 3. Now we have to do the what you call the matrix multiplication, and followed by we have to add them up. So it would be -3, -3, that would be 9. Similarly, here it would be 9, 9, 9. Then you have 1, 1, 1, 1, 1, 1, 1, 1, and then again 9, 9, 9, 9. So if you add them up, it is 18 plus 2, 20. In each of the cases, you'll get 20, 20, 20, 20. So this is what is your covariance matrix will look like. Now, after you find covariance matrix, your next job is to find the eigenvalues for this particular matrix. So to find the eigenvalue for this particular matrix, this is the covariance matrix. Let me just take another page. So your covariance matrix is 20, 20, 20, 20. So we know we have to find the next part is find the eigenvalues. So to find the eigenvalue, what we have to do, let's say this covariance matrix is, let's say it is named as A matrix. So we know that AX is equals to lambda X, where lambda is the eigen. Now, if I have to find the eigenvalue from there, what we have to do, we have to calculate determinant of A minus lambda I is equals to 0. So therefore, it is 20 minus lambda, 20, 20, 20 minus lambda is equals to 0. Now we have to solve the determinant. So this square minus this square equals to 0. So we can see a square minus b square format is there. So I can write 20 minus 20 minus 20. And then again we can write 20 minus lambda plus 20. So over here we can see that these two will cancel each other. So lambda multiplied with 40 minus lambda is equals to 0. And then you can see the lambda 1 is 0 and lambda 2 is 40. So now we can see that we have got two eigenvectors, eigenvalues. So one eigenvalue is 0, another eigenvalue is 40. So in case of PCA, the principal component analysis, what we do, we consider the eigenvalue having highest strength. So over here we can see that which of the eigenvalue has highest strength. Lambda 2 is having the highest strength. So the PC algorithm will choose this particular eigenvalue. So it will be chosen by PC. So therefore, this is the uh, corresponding strength of the principal component. So therefore, 40 is the correct answer. Okay. The next question is stating that after you apply TCA, one of the component. So why I was saying the previous question should be strength of the principal component, because principal component is it is itself a vector. But over here in the answer of in the options, you can see the options are scalar. So counterintuitively, they are asking the strength, not the vector. So there you have to be intuitively correct that as they have given a sort of scalar values in the option. So that means they are asking to extract the eigenvalues, not the eigenvectors. And the eigenvectors are actually the principal components. And those principal components actually imply certain properties. For example, as because you are extracting the eigenvalues from the what you call the covariance matrix. Covariance matrix is a symmetric matrix. And there is a property that, let me just write it over here. Principal component analysis is done based on the eigenvalue decomposition of covariance matrix. And what you do, we calculate the eigenvalue from covariance matrix. Now, covariance matrix is a symmetric matrix. And if we calculate eigenvalue from this covariance matrix, which is symmetric in nature, the eigenvectors, i.e., the principal components, are orthogonal to each other. And this is basically the knowledge from class 12 mathematics, that as we all know that in matrix algebra, that if you have a symmetric matrix and if you are extracting eigenvectors from a symmetric matrix, so the eigenvectors that you have extracted, they will be orthogonal to each other. Now, based on this property that the eigenvector So till this point, we were doing the linear algebra, matrix based algebra. Now, what informative we have got is basically if you extract eigenvectors from the symmetric matrix, your vectors will be orthogonal to each other. Now, if you go to the vector calculus or the vector algebra, so to say, we know that if two vectors are orthogonal to each other, that means their dot product should be zero. So if PCs are orthogonal to each other, then dot product of PCs should be equal to zero. So this is a very important property that you can remember, because many of cases you will see PCA based questions are framed on this particular concept. So over here in the question, they have asked, after applying PCA, one of the component is 0.5, 0.5, 0.5, 0.5. So that means one of the PC, let's say PC1, is equals to half, comma half, comma half, comma half. So this is the vector that you have received. So you have a 4-dimensional data, and from the 4-dimensional data, you have got the principal component. And actually, you have got multiple of the principal components, and you have to identify from the answer that the other components are as given over here. Which of these basically uh, correspond to the other principal components. So what would be the logic to find the other principal components based on the discussion that we have done? So as we just have discussed that PCs should be orthogonal to each other. So that means, let's say this is PC2, PC3, PC4, and PC5. Now we have to see that which of these four basically correspond to the other set of principal components. So as we have discussed, the PC dot product of the PC should be equal to zero, and they are mutual, so I can also write that as they are orthogonal to each other, the mutual dot product. I can write mutual dot product is equals to 0. So that means I have to find PC1 dot PC2 whether this equals to 0 or not. So I have to find this. So now let us find. So if I multiply PC1 with PC2, if we take the dot product, so it is half multiplied with half plus half multiplied with half, then 0 multiplied with half, so 0 and 0 multiplied with half, it's 0. So that is why we can see that this is not equal to 0. So the answer is as because uh, this is actually not equal to 0. So therefore, this is not the PC. This is not PC. So let us now see PC1 dot PC3. So over there as well, you can see that the initial two components would be 0 of the dot product, but later component would be half multiplied with half and half multiplied with half. So again, which is not equal to 0. So the answer is again, this is not a PC. Now let us see what happens with PC, what do you call PC1 dot product with PC 4. So over there, you'll see that half multiplied with half, that is 1 upon 4, then plus 1 upon 4, then minus 1 upon 4, minus 1 upon 4. So therefore, you can see that this is 0. So that means this option is correct. And for PC1 dot PC5, so over there as well, you can see that minus 1 upon 4, minus 1 upon 4, plus 1 upon 4, and plus 1 upon 4. So which is basically again 0. So this option is also correct. So we can see that this 3 and 4 options are correct. So based on this, we can take the correct answer as 3, 4. Fine. So the next question is, you have a data set of two classes. Class 1 has 50 data points with a mean of this and a covariance of this. So let's say class omega 1, it has mu of what you call 3, 5 and the covariance. So I can write cov1 as 9, 3, 3, 6. So here also you can see that as just I've discussed over here that covariance matrix is a symmetric matrix. So over here you can see that these two terms are equal. So that means this is a symmetric matrix. So this is also a counterintuitive part of the previous slide. So here also you can see that for class 2, that the covariance matrix is actually a symmetric matrix. So it is a property of covariance matrix that it has to be a symmetric matrix. So class omega 2, if you consider the mu is 6,8 and the covariance matrix is 12, 4, 4, 8. Fine. Now we have to calculate the between class scatter matrix. So between class scatter so what is the formula for between class scatter matrix? In terms of matrix representation, if you have matrix, if your data is in the form of vector or matrix, then how can you write the formula for between class scatter matrix? I think I have an internet issue today. Okay. So the formula for this matrix is mu1 minus mu2 and mu1 minus mu2 transpose. So you have been given the mu1 and mu2. So you can calculate mu1 minus mu2 easily. So 3 minus 6 and 5 minus 8. And it is 3 minus 6, 5 minus 8. So I have directly written the transpose format. So this is minus 3 and minus 3 minus 3. So if you just do the matrix multiplication, all are 9. Okay. The next question states that dash seeks directions that are efficient for discrimination. So as you can see that the option states that whether it is PCA, SVD, discriminant analysis and L2 regularization. So L2 regularization is a regularization technique that basically helps to either reduce in general, it helps to reduce the values of the weight matrix. And this is used in sort of a learning process. So this has no relation with uh, seeks directions that are efficient for discrimination. So this is a relevant option. The first option is PCA. PCA, actually, the main objective is not discrimination. Its main objective is to reduce the dimension. Reduce the dimension and redundant features. It removes. So this is also incorrect. SVD, singular value decomposition, also helps in data dimension reduction. It has no role in data discrimination, whereas discriminant analysis actually tries to find out the optimal direction for the projection such that it actually does better discrimination among the classes. So therefore, discriminant analysis would be the correct answer. Fine. Next question is, if all eigenvalues are same, then what what would happen. So we know that in case of PCA, what we do, we first calculate the covariance matrix, we do the eigenvalue decomposition, we get different eigenvalues, and then based on the strength of the eigenvalue, we consider some of them. And how we consider the strength? So it is basically, let's say, if you have calculated 3 eigenvalues, we will choose the eigenvalue in such a fashion that lambda 1 greater than lambda 2 greater than lambda 3. So in general, it is lambda I greater than lambda j. So we choose from the highest to lowest. Now in this question, they have written that you have calculated, let's say, and I not equal to j. This is the condition. And let's say I runs from 1 to n. That means you have calculated n number of eigenvalues and lambda I should be greater than lambda j and I not equal to j. So this is the order in which we choose the eigenvalues. Now in the question, they have stated that you have calculated, let's say, n number of eigenvalues and all are same. So that is lambda 1 greater equal to lambda 2 dot 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 lambda n. So if all the lambdas are same, then you cannot choose the particular lambda because in all direction the contribution is same, the variance is same. So therefore, the answer is, the point is basically you are not able to choose specific lambda, which also leads to the fact that you will not able to decide PC. So you'll not be able to decide which PC to consider. So that is the full sentence. So you'll not be able to decide which PC to be considered. As because all the lambdas are same, so you cannot choose that whichever lambda has highest contribution because all are having the same contribution. So therefore, you'll not be able to decide that which PC to consider. And the option is basically that PCA won't be able to select the principal components because all are same. Therefore, you cannot choose which PC to consider. So it is not able to choose the principal components. Right. Okay. In the next question, it states that in PCA, you choose to retain K principal components. So as we just have already told that, let's say you have 3 principal components. So in case of PCA, your main motive is basically to find out that whichever principal component has highest values, you will consider them and rest of them you'll discard. So let's say if you have n number of principal components, if you have n number of principal components, you will choose k number of principal components, which is very, very less than n. So that means what you are doing, you are considering only lambda 1 to lambda k, and k is very, very less than n. So that means you are truncating the information while reconstructing the data, and therefore what you are doing effectively is reducing the data dimension. So actually you are reducing the data dimension. So In this question, the questions yeah, so as I was telling that as you are reducing the number of components in PC, so therefore effectively you're reducing the dimension. So that means in terms of dimensionality, what it is happening is basically dimension decreases. Increases incorrect, remains unchanged, incorrect. This is also incorrect, dimensionality decreases. And the main theme of this particular week was actually data dimension reduction. So intuitively it should be dimension reduction. Next question is PCA is sensitive to the scale of the data. So what do you mean by scale of the data? It is basically whether some of the data is having very large value, some of the data is having very small value. So that means in general it needs the data while processed through any sort of transformation. So PCA is also referred as scale transformation. So if you do any sort of transformation on a given data, you have to check whether the data has any sort of bias or not. So it could be, for example, some of them would have data ranging in very high value, some of them are ranging in very low value. So there might be some sort of discrepancy. So to transform the data, before transforming the data into some another domain or any sort of transformation to be applied with. So we have to go for a normalization technique. Let's say you have certain group of students, you have got their +2 result mark sheets, and let's say group A belongs to state board, where the result is basically given in the form of percentage. And some other board, let's say ICSC. So over there you get in terms of GPA. So in some board you are getting result in terms of percentage, in some other board you are getting result in terms of GPA. Then how to compare these two results? So for that, we have to take normalization. Even for example, in case of GATE examination or NEET examination, wherever in every uh, day slot, the question paper is different. So the person who is appearing from for at day one and the person is appearing at day 2, their questions are difficult. Difficulty level is also different. Question is different. Difficulty level is different. They have got they have got the marks. Now, how to compare the person who is appearing in day 1 and person appearing in day 2? So for that, we need to do normalization. And in GATE exam, there is a particular term called normalization factor, and they have given certain formula for that. For instance, you can see as well. So the main point is basically if you have to do data analysis and if you have to employ PCA, before that you have to see whether the data have any spelling issue or not, and therefore you have to go for a normalization technique. And there are several sort of normalization that is available. For example, min-max normalization, Z-score normalization, which is also referred as standardization. So Z-score normalization you have seen in case of plus two mathematics as well. You have uh, Gaussian distribution, and that Gaussian distribution may not be zero mean standard deviation 1. So to do a zero mean standard deviation 1 distribution, what you do a standardization of the data, and therefore you call the corresponding Gaussian distribution to be a standard normal distribution. So initially you start with Gaussian distribution or normal distribution after standardization. So what is basically meant by standardization? So if you have data, so you have to negate the mean and divide it with the sigma. So this is called standardization. And this is a very generic data normalization technique, which we basically employ before PC. So the next question states that the goal of PCA, the goal of LDA is a maximize within class variance and minimize between class variance. So what we have to do is basically for better classification within class, we have to minimize the class variance. So within class, they have written maximize. This is incorrect. Within class, variance should be minimized. So this is correct. And maximize the between class variance. So that what do I mean? Let's say there are two classes, red. So within class, the variance should be as minimum as possible. So that means they should be as compact as possible. And between class, so between class, let's say blue class, here the variance should be as high as possible. So as high as possible. So that means between class should be maximized and within class should be minimized. So therefore this is correct answer. Option C states that minimize both within and maximize. So this is incorrect, and maximize both. This is also incorrect. So option C is the correct answer. Okay. Okay, so as we have reached the last question, so the last question states that for class independent LDA for two classes, omega W1 and W2. So they for both of the classes, they have given a pool of data points, and these are two-dimensional data points. So this particular side implies the direction of x direction, and this basically shows the values for y dimension. So we have two-dimensional data and we have two classes, and for these two basically belongs to a cluster of two groups. So they have mentioned that. So the new transformation point will be. So what we have to do, so this is a very ridiculous exam question that they have given. So uh, very long vectors, and therefore we have to do very long matrix multiplications. So nevertheless, let us start solving the question. Ridiculous question. So for class one, I have to calculate mu1. So in class one, we have 1, 2, 3, 4, 5 data points. So 1 upon 5. And we have to add 1, 2, 3, 4, 5. And this would be 2 plus 3 plus 3 plus 5 plus 5. So this is so this is 5, 15. And over here it is 3 3 ছয় 10 16 17 18. So 15, 18. So this is 3 and this is 3.6. So for mu2, this is 1, 2, 3, 4, 5, 6. So 1 upon 6, and then 4 plus 5 plus 5 plus 3 plus 5 plus 6, and then 2 plus 0 plus 2 plus 2 plus 3 plus 3. So it is 1 upon 6, and then you have you do 4, 6, 10, 11, 12. And over here we have 5, 5, 10, 14, 5, 5, 10, 4, 6, 10, 20, 25, 26, 27, 28. So this is 4.6, 7, and 2. So we have got the mu1 and mu2 for this ridiculously large matrix. Now we have to get the optimum weight value. So to find the optimum weight value, we need to calculate the scatter matrix. We also have to calculate the between class so we have to calculate the within class and between class scatter matrix. So within class scattering matrices for class 1 and class 2. So for class 1, we know it is x minus mu, then x minus mu transpose, and again over here also x minus mu, x minus mu. transpose. So this is for class omega 1, this is for class omega 2. Now we have to calculate this x minus mu of class omega 1 and class omega 2 one by one. So now let me start calculating them. So for class omega 1 second. So let us start calculating x minus mu first. So x minus mu, it is 1 minus 3 because mu was 3 and 3.6 for class omega 1. And this 3 is for x dimension and 3.6 is for y dimension. So uh, it is 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. Second case, it would be 2 minus 3.6, 3 minus 3.6, 3 minus 5 minus 5 minus. For this ridiculously large matrix, it would be minus 2, minus 1, 0, 1, 2, minus 1.6, minus 0.6, minus 0.6, 1.4, 1.4. So the dimension is 5 cross 2. So it has to be actually x minus mu transpose x minus mu. Fine. So I can write it like this. This is minus 2, minus 2, minus 1.6, minus 0.6, minus 0.6, 1.4, 1.4. And then let me just copy this. I will not write this thing again and again. So let us do the multiplication. Minus 2 whole square minus 1 whole square 1 square 2 square. Then multiply this thing with this ridiculous vector, which is 1.6 to minus 0.6, minus 1, 0, 1.4, 2.8. It will be same here, calculating covariance matrix. This is a symmetric matrix, so I am not going to treat this again over here. Because effectively you are multiplying this thing with this one. So what is the point of writing again the same thing again? But let me just try it. Then over here it would be 1.6 square. I can write minus also because, but I'm just omitting because a square and minus a square are same. Then 0.6 ka square, 0.6 square, 1.4 ka square, and 1.4 ka square. So if you solve this particular thing, you will get, let me just calculate. So if you calculate this, it would be 10, 8, 8, 7.2. You also can check. Okay. Now this is for class omega 1. So we have got the mu and we have got the covariance. Fine. Now we have to calculate for class omega 2. So let me just take another page. For class omega 2, already we have calculated the mu 2, which is 4.67 and 2. Now we have to calculate covariance matrix, which is x minus mu transpose x minus mu. And if I just write it over here, x minus mu first. In this case, it would be 4 minus 4.67, 5 minus 4.67, 5 minus 4.67, 3 minus 4.67, 5 minus 4.67, and 6 minus 4.67. And then what we have over here is 2 minus 2, 0 minus 2, 2 minus 2, 2 minus 2, 3 minus 2, 3 minus 2. So this is minus 0.67, 0.33, 0.33, minus 1.67, 0.33, 1.33. Ridiculous. 0, minus 2, 0, 0, 1, 1. So now let us do the covariance matrix. multiplication. So this is minus 0.67, 0.33, 0.33, minus 1.67, 0.33, 0.33. Then over here 0, minus 2, 0, 0, 1, 1. Then again I have to copy paste this. Now let us do the matrix multiplication, this ridiculously big matrix multiplication. So it is basically square of all the elements and then summation. So 0.67 square, 0.33 square, 0.33 square, 1.67 square, 0.33 square, 0.33 square. And this particular thing is 0 square, 2 square, 0 square, 0 square, 1 square, 1 square. Okay. Then multiplication with this is 0. Then 2 into 0.33, 0, 0, 0.33, 0.33. 2 into 0.33, 0.33, 0.33. Sorry, here is a minus. There is a minus sign. And here is 1.33, 1.33, 1.33, 1.33. So 0.33 plus 1.33. So this particular thing reduces to, let me just write it over here, 1, 1, and over here this is 6, and over here it is 5.33. So we have achieved mu2 as 4.672 and the covariance 2. And we also have uh, seen what are the let me just copy this because I'm not going to write it again. It's and So this is our mu1 and covariance 2. So within class scattered is equals to O1 plus O2 or S1 plus S2, which is 10, 8, 8, 7.2 plus 5.33116. So which is 9, 9, 13.2. Then between class scatter equals to mu1 minus mu2, mu1 minus mu2 transpose. So three minus 4.67, 5.6 minus 2. So this is actually minus 0.67, 1.6, minus 0.67, 1.6. So you can do the multiplication and get the square matrix. It's a 2 cross 2 matrix. The optimum weight. What is the formula for optimum? So your optimal weight is SW inverse mu1 minus mu2. So from the previous slide, what we have seen is your SW is 15.3399 13.2. So 15.3399 13.2. So what we have to do, we have to take inverse. So we have to take inverse. So that means we have to calculate SW inverse is adjoint of SW divided by determinant of SW. So let us now start calculating this thing, which is very odd. And mu1 minus mu2 has already you have seen. So I'm writing adjoint of 15.3399 13.2, and then I can write mu1 minus mu2, which is we already have seen minus 0.67 1.6, so minus 0.67 1.6 divided by determinant of 15.3399 13.2. So if you solve this, you will get the optimum weight. And then after you get the optimum weight, so y is equals to W transpose X. So if you do this, you will get the final answer. And the final answer is minus 1.457. Okay. And there was a last question that if you have, let me just open the spam portal. So in week 7, so the number of linear discriminants that can be obtained in LDA is equals to, it is very obvious that number of class will be the correct answer. So the correct answer is number of class. Okay, so I will be uploading the video as well as the lecture notes on the Drive and in YouTube and Drive respectively. I think now I can stop sharing and as well as stop the meeting as well. We have solved the entire week 7 quiz thoroughly. The week 7 quiz is solved.